let's start our seminar. Seminar 8. And our seminar will be devoted to finding singular solutions. Of differential equation. Singular solutions of differential equations. So the solution is singular. So the function is a singular solution of a differential equation given in the, let it be in the implicit form. If the uniqueness, if at each point, so the function is a solution, is a singular solution, if it is a solution, if it satisfies this differential equation, and if the uniqueness is violated at each point, at each point xy, right? So if at each point there are at least two solutions passing through this point, right? And now our goal is to find singular solutions to this differential equation. Okay, so there are two ways how to do this, and the first way is called p-discriminant, the method of p-discriminant. This means that we need to prove, to solve the following equations. So f of x, y, y prime equals 0, so the original equation, and the derivative of this function, let it be partial derivative df over dy prime is equal to 0. So the function satisfying these two equations is called the discriminant curve. It is called the p-discriminant. So after solving this system of equations, we should first check that this is a solution, but that it satisfies the original differential equation, but it satisfies because this is the part of our solution, right? And next, we should show that we should check that it is singular. So we should find the general solution of this implicit equation, differential equation, and show that at each point of our singular solution, of our candidate to the singular solution, there is some constant, there is some solution from the general family, right, the one parameter family, which goes through the same point with the same slope, which satisfies the same differential equation. Let's consider some examples. Okay, well. So the first example will be the following. So find the singular solutions of the equation 1 plus y prime squared equals 1 over y squared. Well, so just a moment. Okay, right. Let it be this. first of all, let's find the p-discriminant curve. So we should differentiate this equation with respect to y prime. So y prime is a parameter, call it p. So we have the equation 1 plus p squared equals 1 over y squared. And if we differentiate this equation with respect to p, so find the partial derivative of this equation with respect to p, we will get the following. 2p equals 0. If p is equal to 0, then we can substitute it here, and we can find y equals plus or minus 1. Okay, we can check that both, so there are two solutions, y1 equals 1 and y2 equals negative 1. So both functions satisfy the original differential equation. This is step number 1. And step number 2, we should show that they are singular. We should check whether they are singular or not. So in order to do this, we should solve the original differential equation. So let's solve it. So for simplicity, I will solve this for y. So y equals plus or minus 1 over root 1 plus y prime squared. Okay. So for y equals 1 over root 1 plus y prime squared, to find the general solution of this differential equation, I should introduce the parameter p equals y prime and rewrite my equation as 1 over root 1 plus p squared. And in addition, I know that p is equal to dy over dx. And so dx equals dy over p. I should find the differential of this equation. Dy equals p dp over root 1 plus p squared. After this, so dx, so dy will be replaced by p dx equals p dp over 1 plus p squared. And from this equation we have p equals 0 and y, so it implies two solutions plus or minus 1. So they are already found. And if p is not 0, then we can divide by p and integrate both parts. And we have dx equals dp over root 1 plus p squared. Integrating this, we will get the answer x equals ln p plus root 1 plus p squared. Plus c. So not minus, it's only 1, right? So it's case 2-1, and for the case 2-2, when y equals minus 1 over root 1 plus y prime squared, performing the same manipulations, we will get the answer. In just a moment. Okay, so I will substitute, right, I will finish this. So x equals ln minus ln p plus root 1 plus p squared plus c. And y equals minus 1 over root 1 plus p squared. And now we can substitute, we can solve for p and substitute it into this logarithm. Maybe it's better to rewrite it. Just a moment. I think it's better to solve for p, right? To solve for p. It is the same as ln p plus root 1 plus p squared equals c minus x, and p plus root 1 plus p squared equals e to the power c minus x. And we can substitute, so root 1 plus p squared is equal to minus 1 over y, and p is equal to so p squared is 1 over y squared minus 1. P equals plus or minus 1 minus 1 over y squared minus 1. Okay. So too complicated example. So now we should substitute it here. Plus or minus root 1 over y squared minus 1 minus 1 over y equals e to the power c minus x. Right, so this is the general solution. And our particular solution is y2 equals negative 1. And we must show that through any point x and 1, there are at least two solutions passing through this point. So the first solution is our solution. Just a moment. It must be negative 1, right? Negative 1. Negative 1. Okay. And the second solution can be taken from this family of one parameter family of solutions. So we should differentiate this. Just a moment, just very complicated example, I think. Right? Let's differentiate this. It will be multiply by y and then differentiate. I think it would be better. All right. Let it be plus or minus root 1 minus y squared minus 1 equals y times e to c minus x. for y is, if y is positive, but if y is negative, then we must multiply by, so it must be plus, right? I think it's this minus y. Oh, just the same, I think. Let it be minus 1 equals y. And then let's find the derivative with respect to y. And this will give us minus plus y over root 1 minus y squared equals e to the power, it's not this times y prime. Equals y times y prime e to the power c minus x. So I think it's not correct, just a moment. It seems to me that I have mistaken somewhere. Right. So just a moment, I will see. Okay, I think it's not correct. So any differential equation of this form passes through the point. So if y equals -1, then this is 0, and this is 1. So 1 equals e to the power c minus x. And then if c, so it passes through any point x equals c, but since c is any value, then this family of solutions passes, so for some value of c, so if we fix x0, let it be x0. If we fix x0, right, geometrically, this means that we consider this straight line, so and this straight line. If we fix x0, then for c equals x0, there is an element, so a function from this family passing through the same point. But the slope is, of course, equals 0, right? And so it will be some curve from this family, right? So I wanted to show that, so given a solution y equals 1 or -1, and given the general family of solutions, so if we take any point on this line, there is a function from this family passing through this point. But this is, of course, the case, right? Because if we substitute -1 here, we will get this equation, and we are able to find the constant, which is equal to x0, right? So this means that this is a singular solution. Maybe too complicated computations.
You can just substitute y is equal to sin theta and solve this differential equation quite easily.
Maybe y equals to sin theta, right? And solve it. Maybe, right. I see. Yes, I think so. Right. And next, Okay, there is another way. So this is way number one. There is another way to find how to find the singular solution, and it is called the method of C-discriminant. C-discriminant. So using this, what does it mean? So suppose we have the one-parameter family of solutions. Let it be phi capital of x, y, and c equals 0 is a one-parameter family of solutions. Of solutions. So this is the method of finding singular solutions. Right, maybe a new topic, yeah. So one parameter family of solutions. And a singular solution is found as an envelope of this family, right? For example, what does it mean? Do you know the term envelope? What is it? Envelope. Some curve which is tangent to the family of curves, right? It's called an envelope. To find the envelope, we should solve the following system of simultaneous equations, right? Equals 0 and the derivative of phi, so phi with respect to c of x, y, c equals 0. And we must find the solution, and after this check whether it is an envelope or not. Okay, in this case, so let's consider an example. Task number 2. So find the singular solution of the differential equation y equals y prime squared minus 3xy y prime plus 3x squared. And we are given the general solution of the equation. So the general solution is known. It is equal to cx plus c squared plus x squared. Suppose we know the answer. Okay, it can be obtained, of course, using p substitution, introducing the parameter p. So suppose we know the answer, right? How to find the singular solution? So we should solve simultaneously. So the following equations simultaneously. So y equals cx plus c squared plus x squared. And after this, we should differentiate with respect to c. So we get 0 equals x plus 2c. Okay, so we can see, so the second equation is more simple, so we can solve it for c in terms of x minus x half and substitute it into the original equation, and we will get y equals minus x squared half plus x squared over 4 plus x squared. So we can solve, so we can simplify it, and we will get the following. So it will be equal to 3/4 x squared. So this is the answer. So y equals 3/4 x squared. And now let's check whether this is a singular solution or not. So given this solution, we should show that. Okay, so just a moment. 3/4 x squared. Okay, so we should check whether this is a singular solution or not. So given a point, if we fix a point x0 and y0, which is equal to 3/4 x0 squared. Okay, we must show that there is a curve from this family that touch our curve, our candidate for a singular solution. Well, so let's try to find the derivative of this curve. So for the general solution, we have y prime equals, so the derivative with respect to x plus 2x, right? Well, and at the point, so at this point, so let's check the derivatives of our function. So y prime will be 3/4 times 2x, and at this point it will be y prime at the point x0. It is equal to, so I will simplify it, 3/2 x0. Right, and if we return here, right, if we know that so for c, which is equal to minus x half, we have, so y prime equals minus x0 half plus 2x0, and it is equal to 3/2 x0. So we have shown that at this point, the derivative of our particular curve, and for some value of c, the derivative of our general solution are the same. So they go through the same point and they have the same slope. So this proves that this is a particular solution. Well, and now we will try to solve maybe 2 problems, and after this we will finish our seminar. Okay, so I'd like to consider the Lagrange equation. It is an equation of the form y equals x times the derivative, so some function phi depending on y prime plus psi depending on y prime. This is a Lagrange equation, and a particular case of the Lagrange equation is a Clairaut equation. So it is particular case will be this. Well, and let's try to solve Lagrange equation and find, the second task will be to find a singular solution of a Lagrange equation. So it will be task number 3. Y equals xy prime minus y prime squared. So find a general solution and find a particular solution of this equation, this Lagrange equation. Okay. Do you want to solve? So this is a Clairaut equation, right? It looks like this. Okay, who wants to solve? So first of all, you should solve it by the matter of introducing a parameter. Introducing a parameter. Sorry? Like implicit, right? Do you want? Welcome. Here is the chalk. Right. Right, right. You can group them, x minus to p, dp equals 0. So we should consider two cases, right? Right. Okay. And we can solve. So we can solve this for p and substitute it here, and we will get the explicit function, right? Not parametric function, but we may get the explicit answer.
Oh no, it takes.
X squared, right? X squared, right?
Yeah.
And the second case, dp equals 0.
So that means just p equals 0, right?
All right, p equals, so dp equals 0 means p equals the constant, right? Constant, but p is the derivative of y prime equals c, right? So if p equals the constant, then y equals y prime equals c, and y is linear.
This is the end.
So maybe so the last step is to find y, right?
Oh.
So it's better to use this equation. So you should substitute c for p and write the answer for y. Y equals cx minus c squared. So this is the general solution. So the answer is this. The general solution is y equals cx minus c squared and this solution. And after this, we should check whether this is a singular solution or not.
So how to check?
Okay, so how to check this? How to check this? Okay, first of all, we can but I think it will be the same. So let's find the singular solution. I think it should be this one. Using that technique described before, so we know that so the equation y equals xp minus p squared first, right? Next, find the partial derivative with respect to p. 0 equals x minus 2p, right? And solving this simultaneously will give us this solution, right? So this is a p discriminant, and next let's check whether this is a singular solution or not. How to do this? So if we fix any point x0, y0, we should, so on the singular solution, so we take any point from this curve, right? Y equals x squared over 4. If we take any point on this curve, this means that it has coordinates x0 and x0 squared over 4. We should show that there are two curves passing through, at least two curves passing through this point. One is this, and the second is the curve from this general family. And to do this, we should find c, right? So this is a curve, x0. Maybe I will draw the curve, the figure. So it's y equals x squared over 4. This means that this is a parabola. If we take any point x0 and x0 squared half over 4, we should show that there is a curve from this family. So cx minus c squared. Is there any value of c such that this curve passes through this point? Is it possible to find c? So we should substitute x0 squared, right, for y, and try to solve this equation. Okay, is it possible to solve this equation? I think yes. This is a quadratic equation. This is the perfect square. Equals 0, right? So C, x0, but I think we know we need to know C, right? C is equal to x0 half.
Yeah, so x0.
And so we know the curve passing through this point, the straight line, it is the straight line, right? So the straight line having the equation y equals C is equal to, so x0 half minus times x minus x0 squared over 4 passes through the same point. I think it's something like this. Okay. And since both this straight line and this parabola satisfy the original differential equation, because they are found they were found to satisfy this differential equation, so the slopes of these curves are the same. So this is indeed the singular equation. So this is an envelope of the straight lines. So this is the family of straight lines touching, that are tangent to our parabola. Our parabola is an envelope of the straight lines. So we are done. Okay.
Parametric.
Right. So how to find singular solutions? So first we should solve this differential equation, and we will get the family of one parameter, the one parameter family, and some solution. Next, we should check whether it is singular or not. Maybe we have found a solution, but it is not singular. We should show that through any point on this singular solution, so there is a curve in the from the family, from the one parameter family, that goes through any point on this singular solution. And once it is proved, it is shown, then we get that this is a singular solution. Okay. So we have time, we may continue if you want, right? So Kathy, do you want to try? So the next, so it's number 4, y equals 2xy prime minus 4y prime cubed. Okay, find general and singular solutions. Right. Next, we should, okay, our goal is to find x. We should replace dy by p dx, right? Combined terms. Okay. Right, and
Now.
I don't do it.
Right, right. So just a moment. Let's check. I think it's correct, but maybe not. Now our goal is to find x, but it is. I think it is linear in x. Maybe we may do the following. So find x. So our goal is to find x as a function of p. So if we divide by dp, we will get the following: px prime plus 2x minus 12p squared equals 0. But this equation is linear in x, right? And we can solve it using the integrating factor, for example, right?
Okay,
Let's try to do this.
X dash means
The derivative with respect to p, right?
okay.
So our goal is to find x. We can find the integrating factor, so divide by p first. Right. So I remove the integral. Okay. P squared. Well,
Now
so multiply by p squared.
g of x
Right. So it is p, maybe.
Yeah.
It's not x, but p. Because x is a function of p.
Oh no. Yes.
And this is also right.
And so
Not so. It's q of p. Q of p is 12p, right? And we must multiply by p squared and integrate then. So p squared multiplied by p squared, so 12p cubed. 12p cubed, and the integral, right? The integral will be 3 p 4, right, plus c, and after this we will divide by p squared. And so we obtain x. P squared, right? And after this, so we know the, so we know this, right? It's so y. This is a solution: 2xp minus 4p cubed. Okay. And now we need to obtain the singular solution. How to find the singular solution? Just a moment, I will check the answer. So 3, it's, I think it's correct, but so just a moment, y equals 3.
not correct.
So if we substitute x, we may substitute x here, and so y should be rewritten in terms of p only.
P only? Or
So
x? Oh yes, P only.
p, right. So it is parametric, so we can't solve for p, but we may substitute x. P cubed, right? It will be plus C. Just a moment. And it is 2p cubed, right? 2c over p. So this is the general equation, but now how to find the single equation? Right. So we must consider this equation, and we should differentiate it. So find the partial derivative with respect to p, right? And solve them simultaneously. Use that part of the blackboard. So differentiate this with respect to p, and we will get 2x minus 12.
Okay, so what is this? D of?
Dy over dp, right? It is
Equal to.
Okay, and it is equal to 0, right? So, but p squared should be is the constant. So p the root. So, but it depends on c, so it's not good. So it depends on p or on c, so it is not good. But you should, I think you must differentiate this. So it doesn't contain c, and so we should differentiate this equation. So using the I have forgotten about this. So dy over right, it will be
2x minus
2x minus 12 12 p squared equals 0. Right. And now we can solve for p, right? Solve for p. Over 6, plus or minus, right? X over 6, and p is y prime, right? So we can solve
so 1 by 2, 2 by 3.
right. So it's this, and after this we should. Does it satisfy our original equation, right? So I'm not sure. Just a moment. It should be. So let's try to solve simultaneous equation, right? 2xp minus 4p cubed, and 0 equals 2x minus 12p squared. because our so we should solve two simultaneous equations. So x equals 6p squared, and if we substitute it into the original equation, we will get 12p cubed minus 4p cubed. And so x equals 6p squared and y equals 8p cubed. So y equals x to the power 3/2. X to the power 3/2, right? Not. I think. No. So we should substitute, right? So just one equation. No C. Have you found C or not? No. Yeah, I think. So, but if you solve this simultaneous equation, you will get, so p squared equals 6/x and y equals, so we will stop now. So times 6/x to the power 3/2. I think it's the same as, okay, Kathy, this is the solution. So you should solve two simultaneous equations, and this is a solution then. And so after this we will p squared. I'm mistaken. So p squared is x/6 and y equals 8 times to the power 3/2. This is correct. And after this we should check whether it is a singular solution or not. Okay, we will stop here. Let's do it. I will try to. We will discuss it later, next seminar, I think. So bye. See you later.